In the last video, we talked about average velocity as the change in distance over the change in time. And at the end of that video, we asked a question about finding velocity at a particular time, which we call instantaneous velocity. And as promised, we're going to explore that here and see if we can fill in what it means to be instantaneous velocity. So let's again look at the picture from before, where we were looking at the average velocity of our particle whose position was defined by this function, and we were curious about the average velocity of this particle on the time interval from 2 seconds to 4 seconds. And we calculated the change in distance over the change in time and discovered that the average velocity of that particle was 24 feet per second. But what we want to address here is what is the instantaneous velocity at time 2? Well, that's a little bit harder to do because what we used in the average velocity was 2 points that formed a secant line whose slope was our average velocity. And in this case, we don't have 2 points if we want to know the velocity at t equals 2. So let's see if we can explore it further. So here's another picture of our function, and this was the slope of the secant line connecting the point 2s of 2 and 4s of 4, and we know the slope of that line is 24. We discovered that before. Would you agree that if I made that time interval smaller, so let's say P1 is a time closer to 2, so less than 4, and I found its average velocity between on that time interval, that it would be represented geometrically as the slope of that line. Okay, so the slope of this line, which, if I were to draw this triangle, is this change in position over this change in time, would give me the average velocity on this time interval, which is still not exactly what I want. It's closer, but it's not exactly what I want. So let's pick a point even closer, P2. If I were to draw the secant line connecting those 2 points, and it's going to get harder to see the closer I get, the slope of this line represents the average velocity on this time interval, which is still not exactly what I want. But if I keep repeating this procedure, so I pick a point P3, which is even closer than P2, and closer and closer and closer and closer, so I make that time interval smaller and smaller and smaller, then the average velocity becomes closer to the instantaneous velocity at t equals 2. Now, in this picture I came in from the right because it was easier to draw, but I could also come in from the left. Alright, so if I were to pick points to the left on the curve, well, that would represent a different time interval where this time right here is less than 2. And as I made that time interval smaller and smaller and smaller, that average velocity starts to approach the instantaneous velocity at that point at 2s of 2. Okay. So let's see if we can define what that means in terms of some of the concepts we've already talked about. It seems as if the instantaneous velocity at 2, so I'll say v sub 2, that's my instantaneous velocity at 2, is equal to this limiting value of the average velocities. Right? So these, as I make my time interval closer and closer and closer, my average velocity starts to approach my instantaneous velocity. And so that average velocity as these points approach, this is my point P. So that just says that my as I get points closer and closer on either side of 2s of 2, that the average velocities that I'm measuring start to approach the instantaneous velocity at 2. So let's see if we can even further hone in on what this formula should look like. So the velocity at 2 is equal to the limit. So what's my formula for average velocity? Well, I'm going to write s of x minus s of a all over x minus a, right? So this is the y value at, so if this, let's say this point right here is x, and my 2 is a, then as x approaches a, this is my average velocity between a s of a and x s of x, and that's going to be equal to the instantaneous velocity at a. In this case, our a is 2. All right, let's see then if we apply this to our particular example from before, what the actual instantaneous velocity is at 2. All right. So if the instantaneous velocity at 2 is equal to the limit as x approaches 2, so think of your x values getting closer and closer to 2 on either side of 2, of the average velocities, so s of x minus s of 2 all over x minus 2, right? This is the average velocity, so the limiting value of the average velocity as my points get closer to 2s of 2, which is equal to the limit as x goes to 2. Well, s of x is 4x squared plus 3 minus s of 2, which is 19, all over x minus 2. All right, if I were to plug 2 in at this point, I would get 0 over 0, which tells us, if you remember, to do more work. All right, so we come down here and we look at the limit as x approaches 2. 4x squared plus 3 minus 19 is minus 16 over x minus 2, which equals the limit as x goes to 2. I'm going to factor out a 4, and then I leave behind an x squared minus 4 all over x minus 2, which is equal to the limit as x goes to 2, 4 times x minus 2, x plus 2, all over x minus 2. And now I'm ready to do direct substitution. So if I plug in 2, I get 2 plus 2, which is 4, times 4, or 16. So that tells me that the instantaneous velocity at 2 is 16 feet per second. Now, what does that mean graphically? It certainly isn't the slope of a secant line because I only had one point. So if I were to sketch this roughly really quickly, so there's 2. The instantaneous velocity is going to be the slope of this line right here, which is the slope of the tangent line at 2. So the slope of a tangent line, so if we move away from the velocity model and we just talk about the slopes of those secant lines were getting closer and closer and closer to what is our tangent line. So the slopes of the secant lines approach the slope of the tangent line. So geometrically, the instantaneous velocity at A is equal to the slope of the tangent line at A. And that's pretty cool that we have a way to use calculus and limits in particular to be able to calculate the instantaneous velocity of a particle at a particular time. Now, do you think we could apply this to rates of change that are not velocity?